All right, here we go. So today's video is going to be kind of an overview of the rest of the chapter. All right, what we're going to learn is that there are basically two different types of problems that we're going to be solving. There are what are called conservation of energy problems and work problems. All right, and in this video, we are going to be learning the difference between the two. So when you read a problem, you'll know which of those two concepts you need to apply to solve the problem. All right, so here we go. All right, so before I get into this, in the last video we talked about total energy, right? And we learned that total energy was simply just the sum of all the different types of energy. So kinetic energy, gravitational potential energy, elastic potential energy, and then occasionally conceptually we'll talk about electric potential energy, which I called ZPE, and chemical potential energy, all right? But for 99% of our problems, this will be our total energy. And then occasionally we'll tack on elastic potential energy if we have like a spring or a rubber band or something. All right. But the big thing that I want to make sure that I comment on here, I'm worried I didn't stress it very well in the last video, is that to calculate the total energy, you have to talk about the total energy of the object at a certain instant in time. Okay. And you have to pick one instant in time and find the total energy at that instant. All right. So as a simple example, so imagine Roy kicks a soccer ball or something. All right. So here's Roy. Hello. All right, so he's kicking the soccer ball and it's going to go. All right, so if I want to find the total energy of the ball, what I need to do is I need to pick one specific point. All right, so suppose I wanted to find the total energy of the ball right here at this instant. All right, so the idea is at that instant the ball is going to have height, right? Because it's above the ground. So because it's got height, it's going to have some gravitational potential energy. So, suppose we calculated that gravitational potential energy. Maybe it turned out to be 50 joules, right? Okay. Now, the ball is also moving. It's got velocity. That means there's going to be some kinetic energy. So maybe the kinetic energy is, 30 joules. So it would make sense in this instance to find the total energy because that GPE and that KE are both at the same point. So my total energy at that instant is 80 joules. All right? What you can't do is this. I often see students do this. They'll say, all right, he's kicking the ball. It's got a velocity, and that velocity means that it's got kinetic energy. So let's suppose the kinetic energy when he kicks it is, maybe 100 joules. Okay? And then, I wish I hadn't done that. I'm sorry. Just, you don't care, but I'm going to change this to be 80 joules. All right? All right. So, suppose that the kinetic energy when he kicks the ball is 80 joules, all right? And then maybe you find out that up at the top, because the ball is so high up here at the top, maybe the GPE up here at the top is 80 joules, all right? And what I'll see students do then is they'll say, oh, well, that means that the total energy is 80 plus 80 to get 160 joules. But you can't do that because this KE and this GPE occur at different moments in time. All right, so when you talk about total energy, you have to talk about the total energy at an instant in time. Okay, and so the idea is we're going to be talking about two different types of problems. All right, in a conservation of energy problem, whatever your total energy is, it's going to stay constant. Okay, the total energy does not change. So that means that every moment in time, that total energy that you calculate is going to be the same number. All right, now in a work problem, that total energy changes. Okay, and so the goal of this video is to help you understand the difference between those two types of problems. All right, so before we get to that, we got to do a couple quick definitions. All right, so the first thing we need to do is distinguish between the two types of forces. All right, so in this class, we're going to talk about two different types of forces. There is what's called a conservative force, and there's what's called a non-conservative force. All right, so there's a fancy textbook definition of what a conservative force is, and I don't know that it really helps conceptually shed any light onto this. So here's how I'm going to define a conservative force. Basically, a conservative force is a force which is responsible for a form of potential energy. Okay? So gravitational forces are conservative. So gravity is a conservative force because we account for the force that gravity applies when we talk about gravitational potential energy. All right? Similarly, if we account for elastic potential energy in a problem, because elastic potential energy is a form of energy, the force applied by a rubber band would be a conservative force. All right? So for us, here's basically what it boils down to. The only two conservative forces that we're going to talk about only two conservative forces we're ever going to talk about in this class are gravity and then like a spring or a rubber band, okay? Because those are the only two types of potential energy that we'll be dealing with in our problem solving. All right. Now, technically speaking, you could set up a problem to have, you know, a force applied as a result of a battery. You could solve it so that that was a conservative force, or if you had the force from an engine because gasoline is being burned, you could make that conservative. But that's not how we're going to do it. All right. So, for the purposes of this class, the only two conservative forces we're going to worry about are gravity and the force from a spring or a rubber band. All right. Anything else, for our purposes, is going to be considered non-conservative. All right. A little bit of an oversimplification, but enough to give you the gist of what you need for this class. All right. So, kabam. All right. Now we got to talk about work. All right. So here's the deal with work. Work is basically a change in energy. All right. Work changes an object energy in some way, and so what that means is, when you calculate your total energy, we're, for our class, just going to add the KE and the GPE, right? So when work is done, at least one of these three values is going to change, all right? So how do you do work? Well, work is done by a force, all right? You have to have a force to do work, all right? And in order for that force to do work, you have to meet two conditions. Condition number one is this. The object has to be moving, all right? The object has to have some sort of velocity. The velocity cannot be zero. All right. And secondly, there's a typo here that I forgot to fix. All right. The direction of motion cannot be perpendicular to the direction of the force. Okay. So, if you ever had a scenario where your object is moving this way and you had a force this way, then that force is not doing work. All right. A real simple example would be this. If you've got a block sliding along the floor, then there are two forces on it, right? There's gravity and normal force. All right? So neither of those two forces are doing work because the velocity is this way, and both your normal force and your gravity are perpendicular to that. Okay? So in order for a force to do work, you got to meet both of these conditions. The object has to be moving, and the force doing the work cannot be perpendicular to the force. All right. Now, whoops, that's not what I wanted to do. All right. Now, next issue. So it turns out that the work is going to be negative if the force is working against the object's motion. So in other words, if you've got a block that's sliding this way, and the force is this way, that's going to be negative work, because the idea is, the force is working against the velocity, you're going to lose kinetic energy. So a loss of energy corresponds to negative work. Okay? And we'll talk about this more when we learn more, when we do the work video at the end of the chapter here. All right? Now, next issue. If a conservative force does work, then it's just converting either kinetic energy to potential energy or vice versa. All right? Honestly, this point here is really not going to be a big deal for us. But technically speaking, conservative forces just do work to change either potential energy to kinetic energy or vice versa. So we're not going to get too tangled up about that. All right. Now, this next point is the important one, which is this. This is really the whole point of this video right here. All right. If a non-conservative force does work on an object, then it's changing the object's total energy. Okay. That is huge. That is going to be central to this chapter. You have to understand this idea. So put giant arrows and smiley faces and arrows and stuff pointing at this sentence here. All right? If a non-conservative force does work, then it's changing the object's total energy. Very, very, very important idea. All right? So here's the deal. So how do we, when we're given a problem, how do we decide whether it's a conservation of energy problem or a work problem? Well, basically, I put together this little flow chart here that'll hopefully help you figure it out. All right, you're going to ask yourself two questions. Question number one, are there non-conservative forces on the object? All right, if the answer is no, then it's a conservation of energy problem. Okay, which means your total energy is going to stay constant. So if the only forces acting on your object are gravity or a spring or a rubber band or something, then your total energy is going to stay constant. All right? If the answer is yes, if there is a non-conservative force, then you have to ask yourself a second question. You have to ask yourself, is that non-conservative force perpendicular to the motion? All right? Now, if the force is perpendicular to the motion, then again, it's still a conservation of energy problem. Because remember, if you've got your object moving along with some velocity, if your forces are perpendicular, then they don't actually do work. So it's still a conservation of energy problem. All right? But if, on the other hand, you've got an object sliding along and you've got a force that is not perpendicular, then that's when you've got a work problem. All right? So, I think probably where we want to go from here is let's do some examples, all right, and make sure that you're able to distinguish between them, all right? So, all right, so I'm going to give you some different examples here, and for each example, what I want you to do is decide if it's a work problem or a conservation of energy problem, all right? So this first one, it says a ball is falling. So there's actually two circumstances we can look at. So first of all, let's do this. If there's no air resistance, then here's what our drawing looks like. The ball is falling, right? So that means the only force on it is going to be gravity. So if there's no air resistance, the only force is gravity. Let's see. Are there non-conservative forces on the object? Let's see. Gravity. That's a conservative force, right? That's one of our two conservative forces. And that's the only force. So there aren't any non-conservative forces. So that means we land here. It's a conservation of energy problem. So conservation of energy problem. Okay? Now, what if there is air resistance? Well, air resistance is going to push up on the object as it falls, right? Well, let's see. So that's a non-conservative force. Let's see. So are there non-conservative forces? Yes, there are. All right, so let's see. Is the non-conservative force perpendicular to the motion? Let's see. The force is up, the motion is down. Are those two things perpendicular? No. Oh, that means this is a work problem. Our total energy is going to change. The idea is the air resistance is working against the motion of the object, so it's going to lose energy as a result of that. Okay? So, with no air resistance, we land here, it's conservation. With air resistance, it's work. Okay? So, that's a good example because it kind of shows both, both possibilities, all right? And it's pretty simple because there aren't a lot of forces on it, all right? Okay. All right, Sally pushes a lawnmower. All right, so let's do this. Let's draw ourselves a little lawnmower. All right, here's Sally. I'm very close to the camera right now. This is my first time actually recording a video like this with me in the video. All right, so here's Sally. All right, so the idea is she's going to be pushing the lawnmower. The velocity of the lawnmower is going to be this way. And her force, I'm not sure exactly what direction her force is. Maybe she's pushing perfectly horizontally. Maybe she's kind of pushing down the handle. But what she's not doing is she's definitely not pushing straight down, right? As a result, let's see, we've got a non-conservative force. Yes, there is a non-conservative force. Sally is a non-conservative force, right? Is her force perpendicular to the motion? No, she wouldn't push straight down on the mower. So she's going to change the energy of the mower, right? She gives the mower kinetic energy when she pushes it, right? So the kinetic energy of the mower is going to go from 0 to something. So she's giving the mower energy it didn't have before she started pushing it. Okay? All right, Carl holds a cat in his hands. You know what? I think I'm going to skip this example. I don't know that it's super significant. We already talked about the normal force example, and this is kind of the same thing. So I think we're good. All right, friction stops a sliding baseball player. All right, so let's do this. So here's our baseball player. So he's running this way, and he's going to slide into base. He's going to slide feet first. I don't know if that's the best way to slide. I'm not a sports guy, but here he is. All right, so he's sliding along the ground. All right, so there are, I think, 3 forces acting on him, right? Gravity is pulling him down. That's conservative. Normal force, the ground is holding him up so that he doesn't fall. So that's non-conservative, but it's perpendicular. So we're still in conservation of energy land, right? Okay, but friction, oh, that's a non-conservative force. And it's not perpendicular to the motion, right? So this one is going to be work, right? So the idea here is friction puts us here, normal force puts us here, gravity puts us here, all right? But if you have any force that does, any non-conservative force doing work, then there's your answer, all right? So this is a work problem because the force of friction is non-conservative and it does work, i.e. The force of friction is not perpendicular to the motion. Okay? All right. Now, this last example, it says Roy is throwing a ball straight up into the air. All right? So what I'm going to do here, I want to sort of exaggerate this. All right? So I'm going to show you sort of an extreme, for lack of a better word, an extreme example of somebody throwing a ball up in the air. All right? So they have these strongman competitions, right? These big, beefy Norwegian dudes. Oop. Okay, so this dude here that you can see on the screen, he's one of the guys that plays the Mountain on Game of Thrones. Big, strong dude, right? And so what he's got here, this orange thing is a keg. It's a 33-pound barrel, right? And what he's going to do is he's going to try to throw it. I don't know if you can see because the quality on this video is not going to be great, but there's a string up at the top, and he's going to try to throw, or chain or something. He's going to try to throw the keg up over the chain, all right? So notice, right now, the energy of the keg is 0, right? It's not moving, so there's no kinetic energy. And it's on the ground, so there's no gravitational potential energy, all right? So what's going to happen is he's going to do work. He's going to exert a force. Remember, he's a non-conservative force because he's not gravity or a spring. So he's going to do work to give the keg energy, and then he lets go of it, all right? So let's watch and see what happens, and then we'll talk about the physics behind it, all right? So here we go. So he starts at rest. And then he throws it. Notice now the only force on it is gravity. Okay? All right, so there we go. All right, so let's talk about what we just saw there. Here's the deal. There are sort of two distinct parts of the motion. So the first part is this. So the barrel's sitting on the ground, and here's our strong man. Right? And then he's going to throw it. So, hi-ya. Okay? So the idea is, between here and here, there's a force from the strongman. We'll call him Roy. Right? And the velocity is upwards. So from here to here, so while he's throwing, it's a work problem, right? Because there's a non-conservative force, Roy, and it's not perpendicular. So he's changing the total energy, right? But then, after he lets go of it, after release, the ball goes up and comes down, right? But the entire time that it's in the air, the only force on it is gravity, right? So after release, after he lets go of the keg, only force is gravity. So after he lets go of it, it's a conservation of energy problem. All right? So the goal here is, in order for him to get the keg up over, the chain that he's trying to throw it over, he needs to, during this red portion, while he's throwing it, he needs to give the keg enough energy to have enough gravitational potential energy to get it over, well, I guess enough kinetic energy, which will then get converted to gravitational potential energy to get it up over the chain. All right, we're going to revisit this problem with numbers later on. All right, but that's the deal there. All right, so this is actually, there are two different portions to this problem. While he's throwing it, whoosh, it's work because he's a non-conservative force changing the energy. And then after he lets go of it, it's up in the air, only force is gravity. So after he lets go of it, it's a conservation of energy problem. All right, so there you go. That is the difference between work and conservation of energy. The next two videos are going to be focusing on first conservation of energy and then work. And I think having numbers will help sort of tie all this together. All right, so there we go.